a lot. What I'm doing here is totally different from your angle because I don't know much about fractional calculus or fractional order calculus, so I'm here to learn. And ask me and stop me ask questions about if you see anything that your math can be used here. And so I don't have any fractional order here. I'm just talking about what kind of experiment, what kind of project we do. And what I'll do is I have two students here. They will talk after mine. Well, I'll introduce basically one experiment that I think has something to do with the, might have something. It has the flow and the vibration in there. And we have a flow experiment and we have a heat transfer experiment. So I'm going to talk about these three projects specifically to see if we have any application opportunities of fractional order calculus. Now overall, this lab has a name of a thermal and fluid lab, and we do all these projects. These are relevant projects, I think. One thing we do is actually thermal conductivity measurement. It's a property, how fast a solid can transfer heat. So thermal conductivity, we measure at micro scale, and Zilong is going to talk about that. And micro scale is not at the nanoscale yet, 7 microns. So 1/10 of your hair size, basically, you analyze.
Is conductivity,
Yep.
Is conductivity a macroscopic concept?
It's a macroscopic.
Okay.
I think it's a macroscopic concept, yeah. So your conduction of heat is a function of conductivity of the material, area, and the temperature gradient, basically. So these are the three. This is the heat flow, how much heat is flowing through. This is the thermal conductivity.
Okay.
And usually what we do is Fourier's conduction equation here. And we also do develop some kind of a conductivity measurement, unique, and nobody can do that in the world right now, is to measure some of the nuclear fuels, composite nuclear fuels, and we don't have that capability right now in the world. And also, this is actually one step bigger. We're actually trying to develop a technology for the measurement of thermal conductivity in a nuclear reactor. So it's going from small to benchtop to field research. And we also have some other thermophysical property part. One is the electromotive force, and that is the basically thermocouple. How do you measure the thermocouple? The voltage generated by temperature difference. And that is something you can use to calculate phase diagrams and Gibbs function of the material itself. And also viscosity. It's a special measurement for high temperature viscosity measurements, so it's a little different. I'm going to talk about this one, and Zilong is going to talk about this one. And we have also several projects from different applications. One is actually a riverbed. Eli's here, actually. We're trying to develop probes to measure in situ the riverbed thermal conduction along with the flow. And I think that project may also have some potential for because it's a very complex, multi-influence variables, and it's an interesting phenomenon. And also lunar applications, actually talking about the robotic mission to the moon when you measure the heat loss from the moon to space. So you need some kind of a property probes to go in there. And these are NASA projects. Cryogenic, actually this one is the nanoparticles you put into a fluid. So you change, actually in this case is a liquid oxygen. You're putting liquid oxygen. And to change the property, especially thermal conductivity of the liquid oxygen, so you have a superconductive fluid for space applications. And also along with that, this is an Air Force project. It's also liquid oxygen, but you use electromagnetic force to push the liquid oxygen around and use it as like a piston. So it's a pump without moving parts. The Air Force Office of Scientific Research. And the last part is a little different. It has the medical applications. It's the water flow, basically, at micro scale and nano scale. So it's just a pipe flow, but the pipe size is nano size. And in that case, you have surface charge interacting with the water itself. So you have the, again, the equations for the charge, for the electric field, and the flow field three things, interactions in there. And Zori is going to talk about this topic. So let me go to this topic about this particular measurement, and then we go, Zidong will go for this one. There's some kind of a mathematical solution to it, and this is also mathematical. These topics are more, have more math in there, so that's why I picked these. Why this page? What I did is just I copied some pages from different presentations together, so it's not really well organized. This is a measurement system. What it is so-called oscillation cup or transient torque. So what you have is, this is the sample in there. It's sealed in a quartz tube. So what you have is you suspend this sample through a rod, of course, and then you suspend it through a quartz fiber or a tungsten fiber. Now you have a cup suspended with the liquid in the cup. Then you rotate the cup. Because of this wire on top, you have a torsion of this wire. So you have a torsional oscillation. When you look at the oscillation, you measure the oscillation angle with respect to time, you can calculate the viscosity of it. And that's the basic principle. And all the others, you have a furnace, it's a quartz in a vacuum, so it's a vacuum pump. The whole thing is in a vacuum system. And you have actually how do you rotate the liquid is by electromagnetic force. So you have an electromagnet here. And you have high temperature furnace. And this is a quartz and then a rod. And going through, this is a decoder or encoder. You measure very small angular change, so you can see the vibration of this. This portion you consider it's kind of a rigid. And then this is the spring, torsional spring, and you have the viscous damping here. So that's the viscosity measurement. If you look at the damping, if I go back a page, so this is the angular measurement, angle versus time. And it's a long time. Actually, this is about 20 minutes or so. Right here it's 20 minutes, not 400 actually. So you have the angular motion. Based on this logarithmic decay, you can calculate the viscosity. But I'll go back to this. We're not going to talk about this. So here is the model. Two systems. You have liquid, you have a solid vessel. Looking at the solid, you have the solid vibration. So this is a vibration equation for the solid vessel itself. Angle, this is basically MA, or this is the angular. And damping, and this is the spring constant of the rotational spring. And this is the force from the liquid itself. So that's a typical oscillation equation. So you have a spring, you have damping, you have the acceleration force, angular form, and this is the force from outside, external force. On the liquid side, you have a flow Navier-Stokes equation. So this is a transient term because the liquid is flowing first this way and then that way and this way and that way based on the position of the vessel itself. And you have basically R direction only with the viscosity here. And then you have this magnetic force. So outside you have a rotating magnetic force on this, so that's why the magnetic force is over there. So this is the body force of the magnetic force. And then you consider both systems together. So it's solid, liquid, with the boundary condition and initial condition. The boundary condition is that at the wall, inner wall, you have the same no-slip boundary condition. So the velocity of the solid on this side, angle times radius, is equal to the velocity of the liquid. And initially, angle is 0, velocity is 0. Initially, everything doesn't move. So suddenly, you turn the rotating magnetic field on, then you can look at the, so this is the equation we're dealing with, okay? So that's